Okay, so we can have two types, two kind of classification: binary and multiclass. The binary is very easy because we only have two classes, okay? And the multiclass is when we have more than two classes. Okay, it's very easy. But we have another very important distinction that we have to do. We have a distinction between balanced and unbalanced. It's very important because balance is when we have the frequencies of the classes that are equals. In what sense? In the sense that we have, I don't know, in this case, for example, we can have, for example, only images of 0 and 1, and we have the same number of 0 and the same number of 1s, okay? And unbalanced is when some classes are more frequent than other ones. For example, in this picture, we have two kinds of images about an image is about a tumor, and another one without tumor. So a tissue that is healed, and another one that is not healed. So usually we have a very more images of tissues that are not healed. So in this case, we can say that the problem is unbalanced. Okay, is it clear, this distinction? I cannot see you, so okay. And okay, so we will talk today. We will talk. Sorry, I have a problem. Okay, we will talk in particular about balanced classification, but we will do some other general. We will talk about some general concepts that are useful also for unbalanced classification. So, from a mathematical point of view, what a classification is? It's only no, sorry. A classifier what give us a probability to belong to a class, and if we decide a threshold of the probability, we can obtain a label. So, for example, we can obtain a probability of 0.6 to belong to a class, and if we put the threshold of 0.5, we can say, okay, if we are up to 0.5, we belong to a certain class. So the threshold, for example, in a binary problem, is as the name says, it's a threshold that defines when we have a probability, we belong to a certain class. Okay, but we will see later in more details. So a classification is what we call the supervised machine learning problem. So we have an input X, an output Y, and we want to learn the relationship between them. So in particular, the mathematical model is P equal to f of X plus epsilon, where P is an estimated probability of the model to belong to a certain class, okay? So when we are in a multi-class problem, we can have a set of probability associated to a certain, I don't know, image. For example, we can have a probability, we have, I don't know, an image of 0, okay? So we can have several probability that maybe, I don't know, we have 0.8 probability to belong to the class of 0, 0.002 to belong to 1, blah, blah, blah. We have maybe 0.1 to belong to 8. I don't know, okay? And X is the input. So it's, for example, in the first example is X1, X2, or in an image example is the pixels. And we have also another term that we cannot remove that is associated to stochasticity. So an error of a measure, maybe something else, I don't know, something related with the randomness. And F is the relationship between the input and the output. And so this is the algorithm in the end. So this is what we want to learn. So let's see an example. For example, when we are talking about a binary classification, we have two classes, okay? And we say, okay, we have a positive class and a negative class. In this case, we know that the probability sum to 1, okay? Sum up to 1. And so we will use only one term, the p. So the probability to be to belong to the positive class, okay? And 1 minus p is the probability to belong to other class. And this other class is called negative class. An example is the logistic regression. In this case, you can see the implicit form on the top. We have, in this case, two input, x1 and x2. We have three coefficients associated to the regression, okay? And we want to estimate p. So we can explicit p, okay? It's some algebra. We need only some algebra. And in this case, this is the formula, okay? So it's an exponential. And this is the probability to belong to the first class, okay, the positive class. Okay, so let's move on. So the fact is that we want that our probabilities are reflective of the underlying probability of the sample. So what I want to say is, let's take an example. For example, we have a mail that is spam with a 0.2 probability. So we don't know if it's spam or not. We only have a probability, okay? And what we want to see is, let's suppose that we take 5 similar mails, so with similar text and so on. Okay, if they are similars, we want that only one of them is spam, because all these spam mails will have 0.2 probability to be spam. Okay, is it clear, this idea? Because it's the only important thing.
Yes.
Okay, so to understand this thing, to understand if this probability is well calibrated, we will use a calibration plot, okay? And what I want to say is this explanation is only for balanced problems, okay? So it's, we will see it. Okay, so what we have to do to plot, to do a calibration plot is to fix a set of bins, okay, to fix a set of bins in such a way. So we divide it in 0, 10%, after another interval 10%, 20%, okay. And we know that our classifier, okay, has a certain, gives a probability to all the events, okay. So each event in our sample has a probability, okay. In each, and we put, for example, we have a probability of 0.15, and we put this observation in the bin associated between where 0.15 false. For example, 0.15 is between 10% and 20%. So we put this observation in this bin. Okay, so and we do this thing for all the probability, so all the events. Okay, but we suppose next to know what is the real label associated to the event. Okay, so we are estimating the probability in a first step. In the next step, we're supposed to know the probability. If you remember, it's quite easy when if we know what a test set is. So in the test set, we suppose to not know the label, and we estimate the probability, and later we know that what is the label, and so we can do all these steps. So what is the idea? The idea is, okay, in each bin we have a certain number of positive samples. So, for example, if we have if we are in the bin between 10% and 20%, we want to see at least one. We see all the real label, and the real label associated to, for example, to spam, so for example to the positive class, has to be sorry. Let's repeat. We have the events, and we can compute the number of events, so the number of spam mail in this bin. Okay, we know that in this bin we will have no spam and spam emails. Okay, and we will see how many of spam email we have in each bin. Okay, so we count them, okay, in each bin, and we divide them, this count, by the number of observation in the bin, and we call it observed event rate. And so we want that the observed event rate has to be between 10% and 20%. This is the idea, okay? Because this is the same idea that we have explained before. So if we have 0.2 probability that a mail is spam, if we take 5 similar emails, we want that only one of them is spam. Is the very same idea. And so at the end we will have a plot like the orange one. If we are working with a calibrated algorithm. Okay, so and in the other case, with the blue line, we are working with a not well calibrated plot, and in this case, you can see that sorry, guys. We have on the x-axis the different bins, and on the y-axis the observed event rate. Okay. So this is the idea. So we have in the end, we have the probabilities, the probabilities on the x and the observed event rate on the y-axis. And so the orange curve is a curve associated with a well-calibrated algorithm. And the last thing that I want to say about this calibration plot, why it's so important to have a well-calibrated algorithm, because if you say, okay, I have 0.2 probability to have a spam email, we are saying that we are not sure that is a spam. So it's very likely that we are working. This mail is not spam, because so we want to have a very good. That we want that the number associated to the probability makes sense. Okay, so if 0.2 is something like I've just said. So if we take 5 similar mails, only one is spam. Okay, 0.2 makes sense. Otherwise, not. Okay, is it clear? This the calibration plot is the most complicated topic of today, because it takes some time to get it, but it's very important. So if you have some questions, no problem.
Maybe only how to create the line.
Okay, yes, you have to do this thing. You have to fix the bins, okay, and after you have your observation associated to the probability, and you take the probability, and you say, okay, I have 0.15 probability, where I will put this event in the bin between 10% and 20%. Okay, and I do this thing for all the event. After that, I see the real label associated to the probability to each of the event, and I count each of the positive events. Okay, is it clearer or?
Maybe with an example is better because I don't get the point. For example, if I have a mail that is not a spam for sure, where I put this event.
Okay, at the beginning, as you remember, you don't know. Okay, you don't know the real label because we're working with a test set validation one. So you want to estimate with the input if it's a spam or not. Okay, and so you have a probability associated to the spam, and you have, for example, 0.15, and you put this mail in this bin. Is it clear?
Yeah. I thought that it was to understand if the data set was calibrated, not the algorithm. Now I understand.
Okay. Yeah. Any other questions?
Yes, I have one. I don't get the point why, if we have 5 observations and each of them is 0.2 probability, why one of them should be spam?
Yes, because what is the interpretation of probability? Because is the you know that for example, when you roll a dice, so or you flip a coin, you know that the probability is 0.5. So we know when you flip a coin, okay, you flip a coin, and you know that the half of the time you will have a result, and half of the other time you will have another result. So it's the same thing. So if you take 5 similar emails, okay, very similar, and each of them will have a 0.2 probability because they are similar. If the probability makes sense, so if it's related with the reality, you cannot have something different from only one spam email, because it's like you're counting with the probability. What is the probability? The number of positive events under the number of total events. Okay, and so if the total events is the number of similar mails, and 0.2 is so you are saying, okay, I will have 1 over 5 spam email between all my emails. I don't know if
in this case, I think you are talking about in average. Yes,
average. Yes, exactly.
Okay, is this also something that you impose or define, or because
yes, exactly,
it doesn't make sense otherwise?
Exactly. I want that sometimes with, for example, in deep learning, you don't have well calibrated algorithms. It's more related with linear algorithms, random forest, and something easier. But
okay, I get it. Now, one last question: why 0.2 and 5 samples? What not 0.1 and 10 samples?
0.2, if I understood your question, it's because if you do 0.2 is 2 over 10, and so 1 over 5.
Yes.
And so if we take 5 similar mails, okay, no, sorry, maybe it's not 5. I take 5 mails in total, okay? And if I have 0.2, so it's I'm saying 1 over 5.
Yes, but my question is, can it be 1 over 10 and you take 10 mails?
Yes, exactly. Yeah, it's the same.
Okay, so is this a convention? I mean,
No,
5
but
males.
it's only an example. You can take.
Okay.
The idea is in this case, if it's you have to take a very big sample, okay. So you have to be statistical. No, this has to be statistical significant. So
Okay.
at the end, in the end, you have in each bin you have a lot of events with, I don't know, 0.11, 0.12, and they will fall in this bin, and in the end, at the end, if you count the number of events, you divide it by the number of observation, blah blah blah, you obtain the observed event rate, and this the observed has to be similar to the middle point of the bin. So
Okay.
if you are okay, so you have to fall along the epsilon equal to x line.
Okay, perfect. Thank you.
Okay. So now this is the most complicated topic. Okay. So now relax, and we will talk about a very easy topic, that is the presentation of class probabilities, and also the robustness of an algorithm. So when we talk about the robustness of a model is that I want an algorithm that is sure about its predictions, okay? And but it's very simple to show what I want to say. Let's see the example on the left. We are talking about the Titanic dataset, but it's not the important thing. We are talking about a dataset with binary result. Okay, so the result has to be survived or not survived. Okay, and in this case, the algorithm. What we are doing is okay. We have we take a test set and we estimate the probability associated to this test set. Okay, and we split. We do an histogram. Okay, so we know we are in test set, so we estimate the probabilities, but we are in a test set, so we also know the real label. So we split our predicted events in survived and not survived, okay? And we estimate the probabilities of these events. And what we will see is that the positive class, so the survived, in this case, we have a lot of events associated with a very high probability to be survived. And in other cases, we have we are seeing the other probability, so a 0 probability to be survived, so a 0 near 1 probability to be not survived. Okay, so in this case what we are seeing is that our classifier is pretty sure about the decision of the events in the test set, because it's in the end it's dividing. It's pretty very sure about the survived samples, because most of them have a really big probability to be survived, and when we see the other ones, so the not survived, they have a very small to be survived, so a very big probability to be not survived. When we see, on the contrary, the other plots, in this case we are seeing a not good classifier. Okay, in this case the output is a good credit, bad credit. We see a very good probability. In this case, the probability, the positive class is this one on the left. So in this case, the idea is to have the probability of bad credit to be near to 1, and the probability of a good credit is to be near to 0. In this case, our classifier is splitting well is classifying well the good credit, because we have the most of the observations near to 0. But when we see the bad credit, we see that we have a uniform distribution. So our classifier doesn't know what is in reality, not sure about the predictions. Okay, is it clear?
This is the estimated or confronted with the real labels?
Okay, now the real labels, it's used. We have used the real label to split the events between survived and not survived, or bad credit and good credit. After we use the estimated probabilities to plot the histogram. And so, and the idea is, if we are in the survived class, we want a very, very big probability to be of this class. Okay, because we are in the survived class, and if we are sure about what we are saying, we have a very, very big probability to be one. If we are in the survived class, we have a very, very small probability to be survived, so a very, very big probability to be not survived.
Okay.
Okay. Other questions? Okay, let's move on. So now we are starting with this time a very easy idea. Okay. Okay, let's see what we call. Sorry. What we want to understand now is the types of mistakes that we have done, the types of right prediction, and so on. So we want to understand deeply what our classifier is doing. So the easiest and the first and classical idea is the confusion matrix. Okay, what is a confusion matrix? In the confusion matrix, we have on the rows we have the predicted output. On the columns, the observed one. Sometimes they are flipped. So, but if we have some splitted observation, we splitted rows and column, I will say it. But for the moment, we will see that on the rows we have predicted, observed. So what I want to say is, okay, as usual, we have our set with estimated probability, and after, if we take a threshold, we can generate an observation. In what sense? We've seen, for example, in this case, let's come back, that we have used we have talked about probabilities, okay? But we didn't say threshold. With threshold, what I want to say is, okay, for example, we have the probability between 0 and 1, and I use a threshold like, for example, I say all the events with more than 0.5 will be of the first class, so the survived class. And the other one will be in the not survived class. So we decide the threshold. And we have to understand, later we will understand how to decide the threshold. But in this case, we suppose to know what the threshold is. And with the threshold and with the probability, we can estimate the label. Okay? Is it clear, this idea? This is a very, very classical idea behind classification. So let's see your questions. Okay, so it's very, very classical. So the predicted class is when the predicted is the case in which we are saying, okay, I take the input and I predict with my algorithm that I have a positive class. Okay. So after we can compare this result with the real one, and we can say, okay, this is true. So we have a true positive. Okay. Sometimes we can say this is not true, and we have a false positive. So we are predicting an event, so a positive class, but maybe we are dealing with a negative one in reality. And it's the same for the non-event. So we are predicting non-event, but in reality we have a false negative or a true negative. And it's the same with, for example, a test for the COVID-19. Sometimes you have the COVID. You have the COVID, and the test can say, okay, you have the COVID or not. And if it's true, it's a true positive, and if it's false, it's a false positive. And so on the top, we have the general confusion matrix. An example is, for example, below, okay, with, for example, the bad and good credit estimation that we have seen before. And in this case, we have our estimation. We have a 24 predicted estimation as bad, and they are really bad credit. We have 10 bad bad credit predicted, but in reality they were good, and so on. Okay, so this is the idea how to classify our events in the confusion matrix. So with this matrix we can do a very lot of things, and we can build some matrix. Okay. So
vabbè, quando devo cenare smetto.
Andre, sei in...
Sì, adesso ti spengo, scusa.
Okay. Okay. So what we usually build, what we usually use as metric is the accuracy rate. So the idea is when we use a classical machine learning algorithm is okay. Let's see how many true prediction I have done, and I divided them by of the events that I have in my sample. So I sum the true positive plus the true negative, and I divide them by the total number of events. Okay, so this is the classical approach. But the problem with this metric is that we don't know the error that have been made. Okay, because we are not seeing the false positive, false negative. We are only seeing the false positive and false negative in the when you are seeing all the events, but we are not seeing. We don't have some rule, some trick to understand how many of them we have. And in particular, we also have a problem with the frequencies of the class, of each class, because sometimes when we work, for example, with an unbalanced problem can be, for example, a problem when we have for example, 99% of a sample that belongs to one class, okay, and the other 1% that belong to the other class. And let's use a very naive classifier that predict all the events as the most frequent class. In this case, for example, we are saying that the most frequent class is the positive one. Okay, and so in the end, if we say that our prediction is all the predictions are positive, we know that the positive class will be 99%, and our accuracy will be 99%. And so our classifier is not good because it's not studying or understanding what is the relationship in the data, but it's only it's only using the property of the dataset to be unbalanced. So it's not informative. Okay, so the accuracy is not a good metric when we are working with an unbalanced problem. So we can, for example, compute an example. Okay, so in this case, we have predicted we have true positive. You have 300 of true positive, 855 true negative, and 60 and 200 blah blah blah. Okay, so we can compute with the previous formula the accuracy, and we see that we have 85% of accuracy. But as you see, we have a very we have a lot of false negative, but the accuracy is very high. So this is what I said you before. When we have an unbalanced problem, we can have a good accuracy, but in reality our predictions are not very good. Okay, this is so the problem, the accuracy problem. Okay, is it clear? Okay, can move on. So in this case, we use two other metrics. So the sensitivity and the specificity. So in this case, we don't want to use the same equation as before, because when we use all the events, when we use all the events, we are not seeing the differences between false positive, false negative. So we are not seeing the difference between negative and positive class. So we want to change the denominator. In this case, we use we define the sensitivity as the positive samples and predicted to be positive, so the true positive, under the positive samples, so the true positive plus the false negative, because the false negative as predicted as negative, but in reality they are positives. So what is the interpretation of the sensitivity? The interpretation is the ability to detect positive samples. So is when we have a positive sample, we want to understand in a certain sense the accuracy to predict the positive sample if we only see the positive examples. So this is the idea. So is the ability to detect the positive samples, and the specificity is the opposite. So we take all the negative samples predicted as negatives, and we divide them by the number of negative samples. And so this is the ability to detect negative samples. So let's do an example. Okay, this is the same as before. Okay, we take in this case the columns. In what sense? In the sense that the true positive are 300s, and on the denominator we have all the positive, so 300s and plus 200s. Okay, and we have so a sensitivity of 60. Okay, we do the same with the specificity, and we obtain 93. And so now the point is very clear, because we see that the specificity is very high, but the sensitivity is low. It's not very low, but it's, we can say that is low, because we have in the end we have one, maybe almost it's not 50%, but we have almost one real positive example near that is classified as negative. So now you can see that the sensitivity is a and the sensitivity and specificity are two good metrics to see if our algorithm is predicting something, is predicting well our sample. So is this example clear for you? Why we are moving from accuracy to sensitivity and specificity? Okay. Malek, Giovanna, what is it clear, or I have to repeat something? Okay. So if it's clear, okay, we have seen the example, and what I want to explain now is the probabilistic interpretation, because it's very interesting. Sensitivity and specificity are two conditional probabilities. But I think it's clear, because in this case, we are saying, okay, no, let's explain, let's see what is the result, and we will explain later why this is the result. The sensitivity is the probability to be positive to one test from if our confusion matrix is, for example, the result of a COVID-19 test, we can have a disease and be positive or negative to this test. So I will use this terminology from medicine, because it came from medicine. So we can say that the sensitivity is the probability to be positive to a test when the disease is present, and the specificity is the probability to be negative to a test when the disease is absent. And why? The reason is very clear, because we are normalized. We have on the numerator, we have the true positive, so when we have the disease, and on denominator we have the positive samples. So when so on the numerator we have positive sample and predicted to be positive, so when the test is positive. And on the numerator we have positive samples, so when the disease is present. Okay, so this is the very important fact. So in the other case, we have negative test and disease absent. So negative test because we are predicted as negative, and we also be negative, and we have the conditional information because we are normalizing with the negative sample. Okay, so as usual, we have to see this interpretation from the frequentistic point of view. So the true positive is the the positive cases, and the numerator is the positive cases, and the denominator is all the cases. In this case, if we are working with disease present, all the cases are the positive samples. If we are working with disease absent, all the positive cases are negative samples. Okay, this is the probabilistic interpretation, and these quantities only depend on the test. If you got the idea, you can see, okay, this the fact that I have the disease is related to me, and the fact that the result of the test is positive is related to the test. So the probability, this probability is only related to the algorithm, to the test, and so on. So it doesn't depend on the prevalence. What is the prevalence? It's the number in the end of, for example, if we talk about COVID-19, of the number of positive in the sample. So the number of positive samples in all the population. So true positive plus false negative. So, okay. So the sensitivity and specificity is very important, is dependent on the only on the test and on the prevalence, because we will see later other metrics that are dependent on the prevalence. Okay? So, there is a trade-off between sensitivity and specificity, and this is related with the threshold, because, as I've said you, I said that if we change the threshold, we also change the threshold of the probability, we also change the labels. And if we change the labels, we change the true positive, the false positive, the false negative, and true negative. And so we also change the specificity and sensitivity. Okay, so let's see two examples to understand this trade-off. If we decrease the threshold, okay, we increase the number of true positives. Okay, and but the real number of positive is the same, so the sensitivity increases. If we decrease, the threshold, in addition, we also increase the number of false positives. So in this case, the specificity decreases. Okay, because if you remember, we have. If we see the formulas, we increase the number of true positive, but we don't increase the number of false negative, so the sensitivity increases when the threshold increases, and the specificity decreases when the threshold increases. And we have the same discourse when we increase the now, maybe I've said increase before. Now, when we decrease the threshold, we are increasing the sensitivity. When we increase the threshold, we are decreasing the sensitivity. Okay, let's see an example in practice. To see this trade-off, we have to see the ROC curve. Okay, so. In the ROC curve, and is on the y-axis the sensitivity, okay, and on the x-axis 1 minus specificity. So the specificity is true negative under true negative plus false positive, and we do 1 minus this quantity. So it's what we call the false positive rate. So the number of false positive under true negative plus false positive. Okay, and in this plot, we are using the same population, but with different, and within this population, we have the associated probability to belong to the first class. Okay, and we can change the threshold. Changing the threshold, we change the sensitivity and the specificity. So if we start on the top right, okay, in this case we have the threshold equal to 0. So if the threshold is equal to 0, whatever probability we have, all the sample will be predicted as positive. Okay, so we don't have true negative, we don't have false negative. So in this case, we have a sensitivity. We only have true positive, okay, and we have a lot. We have a lot of false positive. So in this case, the false positive rate is equal to 1, and the sensitivity is equal to 1. When we decrease the threshold, we are introducing also the negative class. Okay, we are increasing the threshold. Okay, so you have to imagine this thing. So we are increasing the threshold. So we're moving from right to left. So you can see here the 0.3 threshold. Okay, in this case the specificity is 0.786 and sensitivity is 0.6. So we have this threshold, and if we increase the threshold to 0.5, as you can see, we are increasing the specificity. Okay, because we are introducing more true negatives, but we are decreasing the sensitivity because we are removing the true positive. And so the fact is, the very important fact is that we have to see what we have to understand this trade-off between sensitivity and specificity, and we have to understand what is the best threshold to balance the sensitivity and specificity. So we want to have a good sensitivity and a good specificity. This is the idea. The bisector that you can see, I don't want to prove this thing because it takes one page to prove it, but is associated with random guessing. So when you take decisions at random according to the frequency of the class. So you don't have the bisector is associated with no information. So you have to stay on you want to stay on the upper part of the bisector. The other extreme example is a curve with sensitivity equal to 1, whatever is the specificity. In this case, we have a perfect classifier because we don't have false positive, we only have true positive, and so it's a perfect classifier. Okay, so we want a rock curve that is related, that is the nearest to the line y equal to 1, and this is the point. And when we have to compare different models, we can compare the associated rock curves. Okay, and but usually it's very difficult to compute, to see. Maybe we have a lot of models, so we don't want to see all the rock curves together, and maybe sometimes they can cross, so it's very difficult to understand the result. So if we want to compare different rock curves between different models, what we can do is to compute the area under the curve, what we call RUC. Okay, and this is very interesting because in this case we can select a model between different ones without selecting the probability, the threshold. Sorry. So we only have the probabilities. We don't select the threshold, and we can select. We can choose between different models only according the area under the curve. And so this is a very good method to select a model between different ones. And this is so it's a threshold insensitive, and we also see that is insensitive to the disparity, so the difference of frequencies in the class. Okay, because it's only a function of sensitivity and specificity, and we have said, okay, we don't have the sensitivity and specificity are not related with prevalence, so they are not related with the frequency of the classes. The problem, as I said you, is that the curves could cross. Sometimes maybe the threshold is an important discriminating factor to select the model, and this can you can think that it's in contrast, but with what I said before, but it's not. We have the rock curve is not very good when we are working with unbalanced dataset. In what sense? Before I said, okay, the sensitivity and specificity are not related with the prevalence. It's true, but we will see later that it's true, but there is an influence of the indirect influence of the prevalence. We will see, and we will see later an example. So for the moment, what I want to say is, okay, when we have a very, very, very unbalanced dataset, we don't use a ROC curve. So, is it clear, this example? Is it clear, the ROC curve, why we use it, how to construct it, and so on?
Yes.
Okay, Giovanna, is it clear? Okay, let me see. Okay. Okay, so I'm seeing. Okay. Okay, so this is. So now we have the first. We are not naive as before, because before we at the beginning of the meetup, maybe we're using to select a model only using the accuracy. But we have seen that maybe the accuracy is not a good method, in particular with unbalanced dataset. We will talk in another meetup how to deal with an unbalanced dataset, but I only want to do some tricks, some ideas behind the problems of unbalanced classification. So the ROC curve is the first tool that I give you to better select a model. Okay. What I want to see you, what we will see on the next meetup, working on the Titanic dataset, is that when we are working with a pretty balanced dataset, the threshold from the ROC curve, we will see that the threshold is almost always around 0.5, and it is in fact is the default threshold for the majority of the machine learning algorithms. So okay, and if we don't want to use the AOC and we want to use another. No, sorry. The AOC is to select the model, okay? But, okay, let's suppose that we have a model, okay? We have selected the model. Now we want to select a threshold, okay? Because we have this curve that reflects the trade-off between sensitivity and specificity, but we also want now to select a threshold. How to do it? But the idea is pretty simple. We want to maximize, for example, the Udance J-index. So we want to maximize the trade-off in the end, because the Udance J-index is the sum between sensitivity and specificity, -1, but it's not important, and we want to maximize. So we want the threshold associated to the maximum of this function. So I think it's pretty clear that this is a very good function to select a threshold. In alternative, we can multiply the sensitivity times the specificity. So it's another possibility, and I think that in general we obtain some similar results. Okay, and so this is another alternative. Now let's move on to another topic. The topic is about two other different metrics. The positive predicted value that in machine learning we define them as we define it as precision, and the other one is the negative predicted value. We don't have a term, I think, for negative predicted value, but the PPV is a classical term when we are talking when we talk about medical things. But in machine learning, we usually use precision. Okay, and what is the PPV? Is the positive samples and predicted to be positives, so true positive, under sample predicted as positive. So in this case, we are using the true positive, okay, on the numerator as before, but we are not dividing by true positive plus false negative, but plus false positive. So we are dividing by all the samples predicted as positive. And the same is for the negative predicted value, because we are dividing the true negative under true negative plus false negative. So all the sample predicted as negative. So with the PPV and NPV, we're seeing our prediction is reliable, because if we have a very good prediction, a very good algorithm, we predict a lot of true positive and very few false positive. Okay, so the PPV has to be very high, and this is the same. The same for the NPV. Okay, so let's see an example. So before we have seen that that we have seen the same example. Okay, and we use the 300 as the true positives, and we have divided by 500s. Now, so we have seen the matrix on the column. Okay, we are seeing the column. In this case, when we talk about PPV and NPV, we divided seeing by rows. Okay, so in this case we do 300s divided by 360. Okay, and so in this case we see that the PPV and the NPV is the same. Okay, so I want to give you the probabilistic interpretation as before, the same example as before. So we are talking about we are using the same example of a COVID-19 test, and we can interpret the PPV as the probability to have a disease when we have a positive test. When to have a disease when the test is positive. Why? Because in this case we are using the true positive. Okay, so we are predicted and we have the disease, so we are true positive, and we are dividing. So we are conditioning the information related with samples predicted as positive. So when the test is positive, so the PPV is this conditional probability, and it is the same for the NPV. So the probability of disease absent when the test is negative. Okay, this is the probabilistic interpretation. But as you know, when we have this kind of conditional probabilities, we can see a relationship between them. And the relationship is related with the prevalence 2. So why they are related? From why we can understand how we can understand this idea? Because let's come back to the interpretation. The probability of that a disease is present with a positive test rise when the prevalence is high. So I can have a positive test. Okay, it is objective and is related only with the accuracy of the test. Okay, so with if the test is good or not good, okay, we can have a positive test or negative one. But the probability to have the disease is also related with how many people have the disease in the population. So if I have a positive test, but there are very few people in the population with a disease, it's unlikely that I really have the disease. Okay, so this is the idea. So when we have 90% of the population with a COVID and I'm positive to the test, it's very likely that I have the COVID too. So this is the fact. So this is the intuition behind the fact that the PPV is related with the prevalence, and is also related with the test, okay, because we are conditioning with respect to the positive test or negative one, and so where we can see the relationship with sensitivity and specificity. And to understand better from from an intuitive point of view, I want to do an example. So let's take the same test. So sensitivity equal to 0.90%, specificity 90%, and 1,000 people. Okay, and we change the prevalence. So in this case, for example, the number of positive of the people with the disease from 0.5 to 20%. And let's compute the prevalence. Let's compute the PPV for the two populations. So the prevalence is 5% in the first example, and we have 1,000 people. So we have 50 positive people and 50 negative ones. And so the confusion matrix, so we are sure that 50 people are positive, the 50 are negative, and we also can compute according to the prevalence. So we have seen, not the prevalence, the sensitivity. We have seen that 9 person to 10 are the disease. Okay, so if you compute the sensitivity and the specificity for the confusion matrix, you can see that the right number of the confusion matrix are these ones. Okay, with this prevalence. So the prevalence with also the sample define how many positive and negative peoples we have. The sensitivity and the specificity define the number of true positive, false negative, and true negative. Okay, so we can compute now the PPV. Okay, and we see that the PPV is 32%. And we see that is very low. Let's move on the second example. The prevalence equals to 20%. In this case, we have 20%, so we have, let's remember that we have 1,000 of people, so we have 200 of positive people and 800 of negative ones. So according to the sensitivity and the specificity, we create also the confusion matrix. And let's compute the same, the PPV. And we see that the PPV is 69%. So with the same test, but see a different population, so with a different prevalence. Oh, sorry, the prevalence in the content is wrong because it's 20% and not 5%. And okay, so we see that the prevalence is high, so it's quite good. So we see that the test is the same, so the sensitivity and specificity are the same, but the PPV is related with the prevalence. So okay, so changing the population to another one can change the PPV, and so the precision. Okay, so this is a proof of this relationship. I will. We can use. We will not go into details, but we can use the bias theorem to prove it. Okay, I will put these slides on the meetup group, and you can see the proof if you are interested in. But in the end, at the end, we can see that the relationship is this one. So sensitivity, this is a nonlinear relationship, okay? And you can see the relationship between the prevalence, sensitivity, and specificity, okay? So, okay, we have said PPV strongly dependent on the prevalence, and the fact is that when we're working with a spam classifier, maybe during we can have some troubles because in the next years, maybe we have new schemes to invent spam. So also the prevalence of spam emails can change. So a classifier that can be very, very good in one moment cannot be good in another one. So if this is what I want to give you today. The fact is that if the prevalence, so the frequency of the classes change, the changes, also we have to change in general the classifier too. And this is not the only fact. Is in particular in medicine, the prevalence can also change, for example, according to the geographical position of the people. So if we change from Europe, America, Africa, Asia, and so on. So it's very difficult to use only one test. And so the fact is that we have said before that the ROC curve, so the precision and sensitivity, are not really good when we are working with a very unbalanced data set. Now we will see why. So if you have some question about the previous topic, is the moment. Is it all clear? Did you got the point? Guys?
In my opinion, yes.
Okay. Okay. So let's see.
Yes, more or less it's clear. Can you show the last plot? I think it was in orange.
The last plot, this one. This one.
Yes.
No, it's the next plot now. The precision recall. It's not the plot. It's not related with this topic. It's not related with sensitivity and specificity. It's another one.
So
okay, I have to explain it. So what I want to say is only that we have introduced two other metrics. Okay, they are better than only the accuracy. In this case, you can see four metrics because we see also the PPV, and you see that they are using the confusion metrics. Okay, you have seen how to compute them, and okay, so now it's clear. So let's move on another curve. So we have introduced the PPV that now we will call precision because it's a more machine learning term. And there is a trade-off too between precision and recall. What is the reason? The reason is that the precision is related with, let's come back to how many positive samples and predicted how many events we have predicted as positive and they are really positive over the number of predicted positive sample. So in this case, if we want to reduce if we want to increase the precision, we have to reduce the number of false positive. Okay, but if we have in our mind to reduce the number of false positive, we have to increase the threshold. Okay, because if we increase the threshold, so we are increasing the minimum of the probability to predict an event as a positive class. Okay, so we are saying, okay, let's increase the threshold. So if we increase the threshold, for example, we pass from 0.5 to 0.9, we know that maybe all the events around 0.9, we are pretty sure that they are true positive. So in this case, we increase the number of we decrease the number of false positive, okay, and the number of true positive is pretty the same. So in this case, the precision or the PPV increasing the threshold. But if we increase the threshold, we are also losing a certain number of positive examples, positive samples. So in this case, if we increase the threshold, we increase the number, so we decrease the number of false positive, and so we increase the precision, but we lose a lot of positive example. So we decrease the sensitivity. So there is a trade-off between the sensitivity and precision that you can see in this curve. So in this curve we are plotting a precision recall. The recall is the sensitivity. So we have the recall or the sensitivity in the x-axis and the precision on the y-axis, and we have no information algorithm, so as before, random guessing or something else, and we have a logistic classifier on the orange curve. Okay, and we see that in this case we can see the trade-off between recall and precision. Okay, so also in this case we can select a model seeing the precision recall curve. Okay, so we can see the area under the curve. We can take the model associated with the highest area under the curve. Okay, as before, as in the rock example, and also in this case, after we can be interested in the threshold. So what is in this case the function that we want to optimize to select the threshold? The function that we select is the F1 score. Okay, it's defined as I don't remember. Maybe it's called the geometrical mean. So in this case, we want to maximize the precision and the recall. We want to maximize both, and in this case, we are searching the threshold that maximizes the F1 score. But one last thing that I want to say about this maximization is that sometimes maybe we're more interested in precision and not in recall, okay? Because, for example, sometimes it's more important to be very sure about the fact that we have a positive example with respect to predict all the example that have to be predicted. So sometimes maybe we are more interested in precision or more in recall. Some other times we are interested in some trade-off, and we can use the F1 score to select the best threshold. So the point is, in the end, why this curve is better for very, very, very unbalanced dataset. It's very unbalanced dataset is, for example, when we have we have a scale of 1 over 100. For example, we have 10. All the time we have 100 of negative sample. We have only one positive sample. Okay, and in this case, we suppose that the prevalence is known and is constant, so we are not changing the prevalence, okay? So in this case, why is not good a ROC curve? Because if you remember, we are using the false positive rate, so 1 minus false positive, 1 minus specificity. In this case, we are using the ratio false positive under true negative plus false positive. But the true negative sometimes have a very different order of magnitude with respect to the true negative. So let's see an example. Let's take this example. For example, the negative class. In this negative class, we have this in order of four as negative true negative. The true positive, in the true positive case, we have 2 order of magnitude. We have less than 2 order of magnitude, okay? And if you take the false positive, we have 1 less magnitude, okay? If you compute the sensitivity, you see that we have 0.94, and the specificity is 1/1.95. The precision is 0.035. And this is related with the fact that the false positive are a lot, okay, with respect to the true positive. But the fact is that we are working with a very, very unbalanced data set, and so the false positive are few with respect to are very, very, very less than the true negative. So the ROC curve is insensitive to the false positive. Okay, this is the point. It's very insensitive to the false positive. So you cannot appreciate the difference. So you cannot appreciate the mistakes done by the algorithm. So in this case, when you have a very, very, very unbalanced data set, you have to use the ROC, the precision recall curve to select the algorithm and select the threshold. Okay, but you have to remember that if we change the prevalence, we also change the precision. This is what I want to say you today. So this is the fact. So what I want to say is thank you for your attention. We have finished with the theoretical part. So in the next meetup, we will see the practical example. So we will see how to apply all this theory. Today, I only want to show you the theory behind. And I hope that you got the point, the very important point, that you have to understand the mistakes that you have done, because sometimes they are very, very important. In particular, for my work, I have to understand if I'm doing false positive or false negative when in my usual job. So this is very, very important for a lot of point of view. But I know that now it seems very theoretical. In the next meetup, we will apply all this topic to the Titanic dataset. Is a balanced problem. Okay, so we will not see all the problems that I said you today about the ROC, precision recall, and so on. We will see it in January or February, this problem. But I swear that we will see it. Today we have seen all the theory that we will need in the next meetups. So if you have some questions, it's the moment.
Okay, I have one, and it's regarding the precision.
Yes.
What would be the optimal precision?
Sorry.
What can be the optimal precision? I mean, in the perfect case.
In the perfect case is 100%, because you are only predicting true positive and not false positive.
Yes, but here we have 0.035. So
is not a good precision in this case.
Yes, okay, that's what I'm.
That's the point. In this case, you have a very good sensitivity, so you are seeing all the true positive. This is the point. You're seeing all the positive sample, almost all the positive, but you also seen a lot of false positives. So your threshold is in this case is too low, okay? Because this is the point. So you have to increase your threshold because you have too much positive. Okay. And so in this case, it's not a good classifier because, okay, you can predict, you can see a lot of positive samples, okay, but you are not sure that a lot of them are really positives because the precision is very low. This is the fact.
Yes.
Because
Yes.
if you remember the probabilistic interpretation, the PPV, so the precision, is the probability of to be a true positive, okay, to have the disease when you are predicted as positive. If the precision is low, the probability to be to have the problem, so to be of a certain class when you are predicted as belong to this class, if this probability is very low, okay, you know that between all these positives, some of them are positive, but you don't really know what of these one are true positives. Okay, this is the point.
Okay. And this actually happens because of the difference of order of magnitudes, as you mentioned, right?
Exactly. Because as
Okay.
you can see, it's not possible from the ROC curve, because the sensitivity, as you can see, is very high, the specificity too. But as you can see, we have a big difference in the data set between the two classes, okay? And you can see that it's impossible from the to see the difference, to capture the false positive rate, because the true negative are too much. It's impossible to. So we have to use for a very unbalanced problem a precision recall curve.
Okay.
And so I thank you for, in particular for Hani, because I've seen all this detail about precision recall curve with Hani. So thank you because I don't know them. I didn't know them before.
Problem.
So have you other questions?
No.
Julian,
It was
share
clean, by the way.
the
Thank you.
slide with everybody, with everyone.
Okay. Paolo Francesco, can you share the source of this fantastic topic? Yes, you have all the references on the meetup event. In particular, sorry, I don't want to. Sorry. In particular, this book is fantastic, but you have the reference. Okay, I don't think that you can read the title. Reversed, okay. It's called Applied Predictive Modeling. It's written by the person that they wrote the current package that is the scikit package for R. So it's like you have the package, the author of scikit-learn in a book. So it's a very important book with a lot of examples or a lot of code in R, but in the future I will translate all the code in Python. Now I don't have the time to do it. It's easier to put the code in R. But as you will see the next time, I've done a notebook for the Titanic problem. It's in R, but it's not a problem because I have a lot of picture, I have a lot of discussion, and it will be very easy. It will be very easy to understand how to translate all the code in Python if you want. It's very easy. But in the future, I will do the code in Python. So, no other questions? I've said applied predictive modeling, but if you want to understand the basics of classification problem, I suggest you an introduction to statistical learning. And for the Python code that I'm reading this book, it's end-ons on machine learning and TensorFlow. Or TensorFlow, scikit-learn, something else. In any case, a very huge book, but it's very interesting because you have a lot of code. You have the theory, but you have also a very big part of code. So you can see what I've done today in Python on hands-on on machine learning with TensorFlow and so the theory is in applied predictive modeling, and I I have seen some other references. For example, the problem associated with the ROC curve is in on a notebook in Kaggle of a person that of a guy that I don't know, but I put the references on the meetup in any case, so no problem. All the books that I've used are completely free on the PDF mode, so you can find applied predictive modeling and so on, and introduction to statistical learning online. If you want, you can bring the book, no problem, and you can buy the book. Sorry, and okay. So for me, it's enough today. We will, if you want to see the practical application to a balanced binary problem, a complete approach of on a classification problem, we will see on next Monday, same time. And bye bye, guys. Thank you to be here.
Thank you, Julien.
Thank you.
Bye.
Thank you.
Bye bye, guys.
Bye bye.